Hello everyone, in this video I explain some application problems for derivatives. We're going to use the derivative rules that we did in the previous video for solving these problems. Take a moment to read the first problem and then we can do it together. In this problem, the frequency phi of a simple pendulum depends on its length L, and they're related using this function where g is the acceleration due to gravity, and we need to find d phi over dl. So this means we need to find, so what does d phi over dl mean? So instantaneous rate of change of frequency with respect to length. Or in other words, we can say that how fast is the frequency changing for a given length. So in order to find this, we need to analyze the equation first. So in this equation, you will notice that, so g is the acceleration due to gravity. So g is a constant, and also 2 pi is a constant. So that means the frequency is dependent on L, so phi is a function of length. So I'm going to rewrite the given equation so that we can take the derivative easily. So the given equation is phi is equal to 1 over 2 pi and g over L. So square root, I'm just writing raised to the power half. So if you recall, previously we learned that if you have derivative of a constant times a power function, so you can write this as derivative of power function only times the constant. So constant you can take out of the derivative. So in this case, we know that 1 over 2 pi is a constant, and also square root of g is a constant. So I'm going to bring all the constant terms outside, and then we're going to take the derivative of remaining term. So rewriting this, we see that 1 over 2 pi times g raised to power half. So this is our constant. And the only variable part that we have here is this one. So this is our x raised to power n form or the power form. So in this case, L is a variable. So we have L raised to power, L raised to some power. So now we're going to take the derivative with respect to L on both sides. So we notice that d phi over dl is equal to derivative of 1 over 2 pi g raised to power half, L raised to power negative half. And in the next step, we can write, so 1 over 2 pi g raised to power half outside because it's just a constant, and then derivative of L raised to power negative half. We can combine the factors, so we get negative 1 and 2 pi times 2 is 4 pi g raised to power half, and we can write this as L raised to power 3 over 2. So we can make the power positive in the denominator using our rules of exponents. And if you want, in the next step, you can, so this is like optional, so you can write 1 over 4 pi, and you can write this as square root of g over L cube. But even if you just leave your answer here, so that is good enough. Thus, the frequency is changing at this rate. So negative 1 over 4 pi square root of g over L cube. Or you can just write your answer in terms of fractional exponent form. Let's take a look at the next example. Feel free to pause this video and read the example. We are given that the number of bacteria in thousands, so n is in thousands, is given by, so it's dependent on the time. So this is a relationship rate given by this equation, and the time is given in hours. We have to find the instantaneous change of n with respect to t when t is 6 hours. So here n is a function of t. So basically we need to find dn over dt, or in other words you can say we need to find f prime t. So differentiating n with respect to t we get, so using the power rule, so the derivative of t cube would be, so bring the power down, reduce the power by 1. 3t squared, similarly negative, so 20 is just a constant which is multiplied with a power function. So constant times derivative of t squared, which would be 2t, and similarly plus 100, and derivative of t is just 1, and then plus 0. So overall we got dn over dt is 3t squared minus 40t plus 100. So in other words, your function derivative of n is 3t squared minus 40t plus 100. In the problem, we are asked to find this instantaneous rate of change when t is equal to 6 hours. So now we're going to plug in the value of t equal to 6 here. So we get instantaneous rate of change of number of bacteria when t equal to 6. So just plug in 6 everywhere. So replace the input by 6. So 3 times 6 squared minus 40 times 6 plus 100. So when we calculate this, so we get 36 times 3 minus 240 plus 100. So we get negative 32 in the end. So when time is 6 hours, so instantaneous rate of change of bacteria is these many, but remember, so this is in thousands, right? So times 1000 per hour. So 32,000 bacteria are decreasing per hour because this is negative slope. Negative slope indicates the decrease. This is what was asked in the question. So instantaneous rate of change of bacteria at 6 hours is, so it's decreasing at a rate of 32,000 bacteria per hour. So now we're going to take a look at the graph of n and the derivative of n, and we're gonna do some analysis, and we're gonna learn few things about the function and its relation to its derivative. So before we jump on to the graph, so we can ask ourselves a question. Is there a time when the rate of change is 0? So it means all we are thinking about is when slope is 0. And if we think about the slope of a tangent of this curve, so we notice that at the highest point here, the slope would be 0 because the tangent line would be horizontal, or even at the lowest point, the slope would be 0 again because we have a horizontal tangent. So if we have to calculate this algebraically, so we can say that yes, there would be a point when the slope is 0 or when the rate of change is 0. And if you want to find that, you can put your derivative, which is 3t squared minus 40t plus 100 equal to 0, and you can solve this quadratic. So for solving this quadratic, you can either use your calculator or you can use the quadratic formula. So when we solve it for t, so we find using the calculator that the slope is 0 when t is 10 hours or t is 3.33. So it's just gonna repeating itself, so 3.333 hours. Let's take a look at the graph of number of bacteria and the change in number of bacteria together. In this one, so we already talked about when would the slope be 0. So the slope will be 0 at the highest or the lowest point, and even from the graph we can notice that so it becomes 0 when the time is approximately 3 point something, and also when the time is 10 hours, then the slope is 0. So this is our graph of function. This is our graph of derivative of the function. So if we do the analysis between 0 to 3.33, so this time, so we notice that, so here we have increase in population. Number of bacteria are increasing. So we have increasing function from 0 to 3.33 hours. And we notice that, so this is increasing. And if we talk about the slope, so at 0, this curve near 0, so here it is the most steep. So if you have a tangent at this point, so it means it's going to have the maximum slope here. As we go along the curve, and we see that if we draw a tangent here, so it's going to be again, it's going to have a positive slope, but it's going to be less steep. So slope is positive, but it is smaller. And again, if we go here, so if you draw a tangent line at this point, so let's say this one, so again the slope is positive, but now it's even less steep, so it's gonna even smaller in magnitude. So that's why our slope is decreasing. And when we reach the highest point, our line, tangent line becomes horizontal and the slope becomes 0. So this was 3.33. And we notice that between 3.33 to 10, our function is a decreasing function here. So the population is decreasing. And if we analyze the slope, we see that the slope is negative. So for the portion when the function is decreasing, the slopes are negative. So negative slopes indicate the decreasing function. And even here, so you will see that it has a maximum negative around this point. So here in between here, so it's maximum steep, so it's gonna have a maximum negative power. And then the steepness decreases, so does the magnitude of negative decreases. And eventually the slope is increasing now, so it becomes 0 where it crosses the x-axis again when we have time equal to 10, and then it starts rising. So function starts increasing and the slope becomes positive. Thus, when the slopes are negative, the function is decreasing function. And when the slopes are positive, so positive slope indicates the increasing function. Negative slope indicates the decreasing function. Thus, based on this discussion, we can make some conclusions about a function and its derivative. So the sign of derivative over an interval tells us about the nature of the function, whether the function is increasing or decreasing. So it means if the derivative is positive over an interval, it means the function increases over that interval. On the other hand, if derivative is negative over an interval, it means the function f(x) decreases in that interval. I hope you enjoyed this video. So you can subscribe to the playlist Basic Calculus for more videos in this course. Thanks for watching.